All right, so we already know that to get this expression, we can use our AMGM inequality with something like, if we want x plus y and y plus x, we'll use the square root of x on y and the square root of y on x. Now we know that that all squared, of course, has to be greater or equal to 0, and when we square that, we get the x on y term, we get the y on x term. We also get minus 2 lots of x, y on y, x, so of course they cancel and you get a 1 there. So we do get our x on y plus y on x is greater or equal to 2, which is what we wanted. Alright, so just keep that in mind because we all probably have to use that, otherwise they wouldn't ask it. So part B, hence, yeah, and it's got a hence, so clearly we're going to use it. Prove by induction. Alright, so let's just have a look at P of 1. So, let P of n represent proposition. P of 1 would just be A1 times 1 on A, which of course is 1. And on this side we're getting 1 squared. So it's actually the equality. It's going to equal each other in that case. So P of 1 looks good. So the assumption is the P of k. So we're assuming that for some integer k, that the A1 plus A2 all the way to AK times by the 1 on A1 all the way to the 1 on AK is greater or equal to k squared. So we're going to use that as well. So what do we have to prove? So P of k plus 1. So that would be the A1, A2 all the way to AK and including AK plus 1. And times by A on 1 plus A on 2 plus 1 on AK and 1 on AK plus 1. And we have to prove that's greater or equal to k plus 1 all squared. Alright, so if we take this left-hand side, and because we know we want to use the k, let's use the k, the P of k. So if we go from A of 1 up to A of k, sorry, I'm just writing the first two terms because my pen's not going to work very well. And again, all the way up to the 1 on that. So what's missing if we do that? So we've done that bit times that bit. So we still have our a to the k plus 1 in this bit. A k plus 1, I should say, not a to the k plus 1. A k plus 1 outside of all this stuff. So let's go 1 on A1 plus all the way. Let's just go up to AK. We'll put the k plus 1 separate. So that's all of that. So all the way up to there. So we still have that one. And then we still have this one times everything in that bracket, or the k part of that bracket. So we still have the A1 to the AK and times by that AK plus 1. And then the last bit we have is the last two terms, that one times that one. But that is just a to the, I'll just put it here, AK plus 1 all on AK plus 1 times 1 on AK plus 1. So that's just going to be 1 anyway. Alright, now we can use our P of k. So we know this is greater or equal to, we're putting in this one, for all of the k parts. So we're saying that's greater or equal to k squared. But we've still got our AK plus 1 with the bracket A1 up to 1 on AK there. We've still got our A1 plus all the way to AK, 1 on AK plus 1. And then we've got that last term, which is 1. So it's just run into each other, so just be careful there. Alright, so we've still got that. Now what is that equal to? So we've got the k squared. Now if I take, for example, the A, if I separate these terms, so I've got A, because remember I'm trying to use this. So if I take that AK plus 1 on the A1, and at the same time take this A1 on the AK plus 1, then it looks like x on y plus y on x. And then if I take the next one, so again, this next one would be a k plus 1 on a2, and this next one would be a2 on a k plus 1. So if I keep doing that, right up to the last one, so I've got a k plus 1 on ak and ak, so this last one on a k plus 1. And then, so that's all of those, and then of course I've got plus 1. So I'm just separating out the terms so we can use part A. So using part A, we know each of those parts is greater or equal to 2. So now we're subbing something in that's smaller. We're going to sub the 2 in for each of those. Now how many 2's are there? So there's 2 plus 2 plus all the way to 2, and then of course we've got that plus 1 on the end. If you think about it, we're going from A1 up to AK each time. So there are k terms there. So k lots of 2's would be 2k. So we can simplify that, and that is, so I haven't been writing, so we used our, in this line here, we used our from P of k. In this line here, we're using our from part A. So just make sure you do note when you're doing things like that, which I haven't done. Alright, so this would be k squared. We've got k lots of 2's and 1, and that is equal to our k plus 1 all squared. So that does give us what we were looking for. We were looking for this line here. So we do get that, so it equals so our inequality is true there. So our P of k implies our P of k plus 1, etc., etc. So now part C, so pretend we've done all that. So part C, we're going to deduce. Now clearly we wouldn't, this doesn't come out of nowhere. It's like a hence, deduce that. So what can we sub in basically to what we found to get what we want? So it's tempting to see that n and go look at that and sub in a 3 cos theta. However, remember this is something plus something plus something. That looks like it comes from one of the brackets. So we've still got the other bracket to kind of contend with. So let's try subbing n equals just the 3. So it's just going to give us the 9 squared. And see how we go. Let's also try, because clearly we want a cosec squared and a sec squared and a cot squared. Now they are the reciprocals of sine squared, cos squared and tan squared. So why don't we try letting a1 be sine squared theta, a2 cos squared theta, and a3 be tan squared theta. Let's just try it and see if it doesn't work. We can try something else. But in the first bracket, you can see we're going to have sine squared theta plus cos squared theta, which is 1, plus tan squared theta. That's actually nice because we know that 1 plus tan squared theta is sec squared theta. And in the second bracket, we're going to have 1 on sine squared, which is what we wanted. So that's cosec squared, 1 on cos squared theta, that's our sec squared, and our 1 on tan squared theta, which is our cot squared. So we know that, and our n is 3, so that's 9. Alright, so let's change this. I'm going to cheat and kind of go, this is a 1, and 1 plus tan squared is sec squared. And sec squared, actually, let's write it as 1 on cos squared. Sec squared is 1 on cos squared. So you can see now where I'm going to get this cos squared from. And then here, 1 on sine squared is my cosec squared theta. So I've got all those reciprocal squareds now, and cot squared theta there. So you can see I'm just going to times both sides by cos squared, and I've still got these 3, and that's now going to be greater or equal to 9 cos squared theta. So it's just about substituting the correct things in to get the deduction.